Welcome back, everybody. All right, today we're going to talk about testing the difference between two means, more specifically with large samples. All right, so these samples, the qualifications are these samples are independent. And what that means is that one sample is not connected with the other. All right. Also, that either the standard deviation for the population is known, or your sample size is greater than or equal to 30. Because if the sample size is greater, you don't need the standard deviation for the population. You can always use the standard deviation for the sample. So this is what we're going to do today. All right, let's start with the formula that you're going to need. It's a little more involved than the formulas we've used in the past. For our z-score, we have x bar 1 minus x bar 2 minus mu1 minus mu2 all over the square root of sigma squared over our first sample size plus our second sigma squared over our second sample size. And that's all under the square root. All right, even though this formula looks a lot different, it still follows the pattern of our test value. So this will get our test value. Right? In the past, our test value equaled our observed minus the expected. And then we divided by the standard error. So if you look at this, right, we see that we have x bar 1 minus x bar 2, which is what we've observed, right? Our samples have these averages, minus the expected, minus our mu1 and mu2. That's what we expect. And then our standard error is our variance divided by the sample size. All right, we are still going to use the same procedures that we used before. That is one of the big keys, is we're not going to do anything different than we've done for the last couple of sections. So our 5 steps to success, we're going to state the hypotheses and identify the claim. All right, we're going to find our critical values. I'm going to use CV for critical values. All right. Then we're going to compute the test value. All right. I'll also use an abbreviation TV for test value. Our 4th step, we're going to make a decision. And our decision is either going to be to reject or not reject. Always the null hypothesis. And then based on that decision, we're going to summarize. Always helpful to summarize, to bring it back, like I said, always to the context of the problem. Probably the most difficult is going to be deciding if it's right-tailed, left-tailed, or two-tailed. But you really need to look at the wording of the problem to make sure that you have it right. All right, so let's start with the first example. A survey in 1995 found that the average room rate in New Orleans is $88.12. The average room rate in Phoenix is $80.61. Assume the data were obtained from the two samples from 50 hotels each, and the standard deviation was $5.62 and $4.83 respectively. At alpha equals 0.05, can it be concluded there is a significant difference in the room rates? All right, so I'd like you to pause the video right now and just think for a second, what is going to be your null and alternative hypotheses? All right, hopefully you've taken a minute to think about it. I decided that my null hypothesis was that the two means were equal. Now, the problem didn't indicate bigger, smaller. It just simply said that the two samples, can it be concluded there is a significant difference? So it didn't say larger, smaller, anything like that. So I'm going to conclude that my alternative hypothesis would be that the means are just simply different. And I'm going to state this as my claim. All right, so now we need the critical value. All right, and the critical value for this, because we have our standard deviations known, as well as a significant sample size, large sample, our critical value, we're going to use the elements alpha equals 0.05. It's two-tailed. Two-tailed test. And I found my critical value to be plus or minus 1.96. All right, so basically what this means is that if I draw my picture, that should be about equidistant. This is the border, and the shaded region is my rejection zone. All right, so now we need to calculate our test value. Now, I'm going to scroll back up for a minute. This new formula that we talked about is going to be for our test value. So take a moment, write it down. Pause the video if you need to, because in a minute I'm going to scroll back down and we're just going to fill in some numbers. All right, so let's fill in some numbers. So let's see, so test value. All right, so that equals, all right, so my first sample was, average was 88.42. My second sample average was 80.61. And then my mu1 minus mu2, right? My null says that they're equal. So the difference between those is 0. And then I have 5.62 squared over 50 plus 4.83 squared over 50. So why don't you pause the video now and do the calculation and tell me what our test value is. All right, hopefully you paused the video, did the calculation. I got 7.45, which, if we look at our graph, is clearly in the rejection zone. It's clearly greater than 1.96. So our decision is to reject our null hypothesis. All right. So once we reject our null hypothesis, right, we rejected that they were equal. So we have supporting data that says that the claim is true. All right. So we can say there is enough evidence to support the claim and you can also then finish the sentence. All right. So we can also use p-values to get our data. Now, again, p-value is not my favorite, but it is a valid way to do this. So let's review our steps for success on the p-value. All right, so the first step is going to stay the same. State the hypotheses. Identify the claim. All right. Now we're going to break off. Now it's going to be compute the test value. The formula doesn't change. So the same exact formula we used in the prior example is the same formula you're going to use to compute the test value. From the test value, right, after that, we're going to find the p-value. Right, so we're going to get that z. We're going to go in and we're going to find out what the area is. From the area from our test value and our p-value, we're then going to make a decision. And then our fifth step is going to be to summarize the results. Always bring your results back to the context of the problem. It's really helpful. It'll really do a lot of good for you. All right, so let's start with an example. All right, here's the next example. A researcher hypothesizes that the average number of sports colleges offer males is greater than the number of sports offered to females. A sample of the number of sports offered by colleges is shown at alpha equals 0.10. Is there enough evidence to support the claim? All right, well, now I have not given you averages and I have not given you standard deviations. So at some point, we're going to have to calculate those. But why don't you think about it just for a second and think about what your null and alternative hypotheses would be. All right, hopefully you thought about it a little bit. I felt that the null hypothesis would be that mu1 is less than or equal to mu2. We're calling mu1 males and mu2 females, right? And then our alternative was that the researcher claims that the male average is greater than the female average. So I'm going to call that my claim. All right, so now we need our averages. So this is, I'm going to call it step A. Call this one step B. I called them 1, 2 before, but we can say, okay, so 4 males. Let's get X bar 1 and S1. All right, we need these for our test value, so we got to calculate them first. So why don't you pause the video and go through and calculate the average. Now here's the key. You have 50 numbers here, right? So our n is going to be 50. N1 equals 50. N2 equals 50. You're going to get that just by counting up the number of numbers. It's key that you don't miss a number when you're doing your average. You don't miss your number when you're doing your standard deviation. That will definitely throw you off. All right, so take a moment, like I said, pause the video and do your averages now. All right, so I found my average for sample 1, the male sample, would be 8.6. I found my standard deviation to be 3.3. My second sample, my female sample, 7.9, not 7.7. I'm going to make that better. And my standard deviation, again, I got to be 3.3. Again, totally key to success here. Because now when we scroll up, we have to use these numbers in our Z formula. All right? So it's 8.6 minus 7.9, right? And then if the mu's are equal, right, we subtract and get 0. Square root of 3.3 squared over 50 plus 3.3 squared over 50. So why don't you again pause the video and let's get our test value. All right, so I got my test value to equal 1.06. And now we need to look for the p-value. So I take my z equals 1.06. And I need area to the right because my alternative says it's a right-tailed test. So my chart gives me area to the left. So I did 1 minus 0.8554, and I got 0.1446, right? And what I notice when I make my decision is that my p-value is greater than my alpha, right? My 0.1446 is greater than 0.10. Therefore, it's not in the rejection zone. All right, we've covered more area. It's outside the rejection zone. So my decision is that I do not reject my null hypothesis. And when I'm making my decision, or when I'm summarizing my results, I always look back to see where my claim is. If I'm not rejecting the null hypothesis, there's not enough evidence to support the claim. So there is not evidence to support the claim. Dot, dot, dot. Again, tie it back in to the context of the problem. Okay, so the last thing that we can do in this section is we can use the difference of two means to get confidence intervals. All right, so we did confidence intervals in chapter 8. But they can come back around again. So so we can do confidence intervals. And they can help us make our decision as well. So I'm going to give you the formula that you need. Is x bar 1 minus x bar 2, which is going to be our observed average. And then I'm going to subtract my standard error, which is z alpha divided by 2 times our variance divided by n1 plus our variance divided by n2. And then the same thing on the other side. We have x bar 1 minus x bar 2. Make it a little smaller. That way I can fit everything in. Z alpha divided by 2 times the square root of our variance divided by n1 plus our variance divided by n2. All right, so you also need to remember that when n1 is greater than or equal to 30 and n2 is greater than or equal to 30, you instead of in place of our variance for the population, you can use the variance of our sample. So if the sample sizes are large enough, you can use S instead of sigma. All right, so I'm going to go back to the problem. So if you need to pause it to reread, I'm going to use the data contained in this problem here, right? Our example 1. All right, so take a moment to reread example 1, maybe copy down some of that data, and then let's do a confidence interval for the difference of the means. All right, we're back. I hope you reread that problem real quick and you got your data that you need. So we're going to use the data in example 1. Right, and find the 95% confidence interval for the difference of the means. All right, and again, I'm going to scroll up here real quick and give you just a minute to take a look at that formula. Copy it down because we're just going to fill in some numbers after this. All right, hopefully you paused the video and copied that formula down. I need the space, so I'm going to scroll up. All right, and we're going to start putting in our numbers. So our x bar 1 was 88.42, and I'm going to subtract 80.61. And then I'm going to subtract my standard error. So my z alpha divided by 2 was 1.96. That just came from the other problem. And then we had our sample sizes were big enough, so I'm going to use my S. 5.62 squared over 50 plus 4.83 squared over 50. And then I'm going to say less than mu1 minus mu2, which would be less than. And I'm going to go to the next line to finish my formula. So it's going to be 88.42 minus 80.61 plus our standard error, which I'm going to put in my 1.96 first, divided by, or square root of 5.62 squared, that's a 6, over 50 plus 4.83 squared over 50. All right, usually I like to do the standard error first. Putting too much in your calculator all at once invariably is going to make a mistake. It will return a value for you. It will just return a wrong value. So let's subtract the 88.42 minus 88.61, and I get 7.81. Now I'm going to do my standard error separately. So why don't you pause the video now? Why don't you try to calculate your standard error, and let's make sure we get the same number. All right, so hopefully you paused the video. I got 2.05, so I'm going to subtract 2.05, mu1 minus mu2. All right. So, and then I have 7.81 plus 2.05. And when we wind up adding and subtracting, I get 5.76, which is less than mu1 minus mu2, which is less than 9.86. All right. Now, how in the world can we make a decision on a hypothesis test from our confidence interval? Well, if we look back at the problem, I'm going to scroll up for just a second, see if I can get there. There we go. If you remember, our null hypothesis was that the mu's were equal, right? And if I subtracted mu1 from mu2 and they were equal, I would get 0. Yes? Well, in my confidence interval, I'm 95% confident 0's not in there. So once again, the same conclusion of do not reject the null hypothesis is valid, because basically what I'm saying is I'm not 100% sure, but I'm 95% sure that mu1 and mu2 are not equal, because then there would be a 0 in there. Now, is there a possibility I'm wrong? Sure. But there's also a possibility I'm wrong doing the hypothesis test the way I did it. So it is a valid way to do it, and it is something that I would definitely consider if the directions led you that way. All right, there's a lot more practice to be had. Thank you guys for listening, and I'll see you next time.